Something is buried under the moon's surface that nobody expected to find. And when China's lunar probe sent back its data, scientists around the world went quiet. Not because the discovery was confusing, but because it was the kind of discovery that rewrites everything. Everything we thought we knew about where the moon came from, how it formed, what it's made of, and what it might mean for the future of space exploration. All of it suddenly had a question mark hanging over it. And here's the thing. NASA has been studying the moon for more than half a century. American astronauts walked on it. Rovers have crossed it. Orbiters have mapped it from pole to pole. The United States has invested more time, more money, and more human life into understanding the moon than any other nation on Earth. And yet, it was China's Chang'e program that found something down there in the lunar soil that American missions had completely missed. If that doesn't make you want to keep watching, consider this. What China found isn't just scientifically interesting. It has direct implications for NASA's plans to return humans to the moon under the Artemis program. It has implications for any future lunar base. It has implications for the global race to harvest resources from the moon. And depending on how you interpret the data, it might even have implications for how we understand the origin of the Earth itself. So stick around, because we are going to go deep on this. And I mean deep, literally. Before we get into what China actually found, we need to establish some foundation, because the moon is one of those things that people think they understand. You look up at it on a clear night, and it seems simple. It's a rock. A big round rock floating in the sky. What's mysterious about that? As it turns out, almost everything. The moon is one of the strangest objects in our solar system. It is enormous relative to the planet it orbits. Most moons are tiny compared to their parent planets. The moons of Mars, Phobos, and Deimos are small enough that you could fit the entire surface area of both of them inside a mid-sized country. Jupiter and Saturn have large moons, but those planets are also colossal, so the ratio is still manageable. Earth's moon, by contrast, is more than a quarter the diameter of Earth itself. In the entire solar system, the ratio of moon size to planet size is unique in our case. We are closer to being a double planet system than we are to being a planet with a small orbital companion. And that oddity has bothered astronomers for a very long time. How did we end up with such a disproportionately large moon? Where did it come from? What is it made of? And why does it behave the way it does? The leading theory for the origin of the moon is called the giant impact hypothesis. The idea goes like this. About 4.5 billion years ago, when the solar system was still young and chaotic, a Mars-sized object slammed into the early Earth. This object even has a name. Scientists call it Theia. The collision was so violent, so catastrophic, that it essentially liquefied both Theia and a significant portion of Earth's outer layers. The debris from that collision, a massive ring of molten rock and vaporized material, was thrown into orbit around what remained of Earth. And over millions of years, that debris slowly clumped together under gravity, cooled, and solidified into the moon we see today. It's a compelling story. It explains the moon's size. It explains why the moon has relatively little iron in its core compared to Earth. It explains certain chemical similarities between lunar rocks and Earth rocks, and it's been the scientific consensus for decades. But there are problems with it. There have always been problems with it. And what China found underneath the lunar surface has made some of those problems significantly harder to ignore. Let's go back to the beginning, the very beginning of lunar exploration. The space race between the United States and the Soviet Union was, among other things, a race to understand the moon. Both nations launched missions in the late 1950s and early 1960s, crashing probes into the lunar surface, flying orbiters around it, and eventually landing rovers and human beings on it. The Apollo program, between 1969 and 1972, returned 382 kilograms of lunar rock and soil to Earth. Scientists have been studying those samples ever since, and for a long time, that analysis formed the backbone of everything we thought we knew about the moon's composition and history. Then the focus shifted elsewhere. Mars became the next great frontier. The outer planets beckoned. Attention drifted away from our nearest neighbor, which had come to seem familiar, understood, perhaps even a little boring. China, meanwhile, was building a lunar program from scratch, and they approached the moon with fresh eyes, new technology, and a very different set of questions. The Chang'e program, named after the Chinese moon goddess, launched its first mission in 2007. It was an orbiter, collecting data about the lunar surface from above. Then came Chang'e 2, another orbiter with higher resolution instruments. Chang'e 3 made history in 2013 as the first soft landing on the moon since the Soviet Luna 24 mission in 1976. Chang'e 4 went even further. In January 2019, it landed on the far side of the moon. The far side, the hemisphere that perpetually faces away from Earth and had never, in all of human history, hosted a landing spacecraft. That mission alone was extraordinary. Getting a lander and rover to the far side of the moon required China to first launch a relay satellite to communicate around the curvature of the lunar body, because direct radio contact from Earth is impossible when your spacecraft is hiding behind the moon. The engineering alone was a massive achievement. But it was what the Yutu-2 rover found once it got there that started making headlines in scientific journals around the world. The Chang'e 4 landing site is called the Von Karman crater, located within a much larger feature called the South Pole Aitken Basin. And here is where we need to pause and appreciate just how significant that location is. The South Pole Aitken Basin is not just any crater. It is one of the largest impact craters in the entire solar system. It stretches roughly 2,500 kilometers across and plunges nearly 8 kilometers deep. To put that in perspective, it would comfortably cover the entire continental United States with room to spare. And it's 8 kilometers deep. That's deeper than any ocean trench on Earth. This basin was created by an absolutely catastrophic impact event early in the moon's history. A massive asteroid, perhaps hundreds of kilometers wide, slammed into the lunar surface with enough energy to blast through the moon's outer crust and excavate material from deep inside. Which means that studying the rocks and soil inside the South Pole Aitken Basin is, in a sense, like doing a core sample of the moon without actually having to drill. The impact did the excavation for you. Scientists had been theorizing about what should be at the bottom of that basin for years, and their models predicted something specific. They believed that the impact would have exposed material from the lunar mantle, the layer beneath the crust. And the lunar mantle, according to our best models of how the moon formed, should be rich in certain minerals, specifically something called olivine. Olivine is a common mineral in the solar system. It's found in Earth's mantle, in meteorites, in the crusts of other rocky bodies. It's greenish in color, and it was expected to be abundant in the moon's mantle. Everything about our models of lunar formation pointed to olivine as the dominant mineral in the deep lunar interior. Yutu-2 drove across that basin and fired up its spectrometer. The spectrometer analyzes what wavelengths of light are reflected from a surface, and different minerals have distinct spectral signatures, like fingerprints. It's a way of identifying what materials are present without actually picking them up and taking them to a laboratory. And what Yutu-2 found was not olivine. Instead, it detected a mixture of minerals called low-calcium pyroxene and olivine, but in proportions that didn't match the predictions. The pyroxene signal was far stronger than expected. The olivine signal was weaker. And that mismatch, that gap between what should be there according to our models and what is actually there, immediately raised a red flag. At first, scientists considered the possibility that the rover was sampling impact melt, material that had been melted and mixed up by the original collision that formed the basin. Impact events create extremely high temperatures, and they can chemically alter rocks in complex ways. Maybe the strange mineral mix was just the product of that ancient catastrophe. But as the data was analyzed more carefully, other explanations started to emerge. Explanations that were harder to dismiss and harder to reconcile with the standard model of lunar formation. Because here's what those mantle minerals tell us, if that's truly what they are. The composition of the lunar mantle is a direct record of how the moon formed and how it cooled. When the moon was young, it was likely entirely molten, a global ocean of liquid rock called a magma ocean. As that magma ocean cooled, different minerals crystallized out at different temperatures and sank or floated based on their density. Denser minerals sank toward the core. Lighter minerals floated toward the surface. The entire internal structure of the moon is a record of that cooling process. The mineral composition of the mantle tells us the temperature at which different layers solidified, the chemistry of the original magma, and the sequence of events as the moon transitioned from a liquid ball of rock to the solid body we see today. If the composition is different from what we predicted, then our model of the cooling process is wrong. And if our model of the cooling process is wrong, then our understanding of how the moon formed may need significant revision. But the story doesn't end there, because Chang'e 4 was only the beginning. Chang'e 5 launched in November 2020 and successfully landed on a region called Mons Rumker in the Oceanus Procellarum, or Ocean of Storms, on the near side of the moon. This was a sample return mission, the first of its kind since 1976. The spacecraft drilled into the lunar surface, collected approximately 1.7 kilograms of rock and soil, sealed it in a capsule, and launched it back to Earth, where it landed in Inner Mongolia in December 2020. Those samples have been studied intensively by scientists around the world, and what they found when they analyzed those rocks was genuinely stunning. The age of the samples was unexpected. The rocks from the Mons Rumker site are approximately 2 billion years old. That doesn't sound dramatic until you compare it to what we previously knew. The youngest lunar volcanic rocks from the Apollo missions were around 3 billion years old. The standard model of the moon suggested that by about 3 billion years ago, the moon's interior had cooled to the point where volcanic activity had essentially ceased. The moon, according to that model, was geologically dead. But here's 2 billion-year-old volcanic rock that formed when lava erupted onto the lunar surface, a full billion years after the moon was supposed to have gone cold and quiet. That's an enormous discrepancy. A billion years is not a rounding error. It's not a measurement uncertainty. It's a fundamental fact about the moon's thermal history that our models got completely wrong. The moon was volcanically active far more recently than we believed, which means the moon's interior retained heat much longer than we thought. Which means there's something about the moon's internal structure and composition that we don't fully understand. And then the geochemical analysis of the Chang'e 5 samples went even deeper. Scientists were trying to figure out what could have kept the moon hot enough to produce volcanic eruptions 2 billion years ago. Heat in planetary interiors comes from a few sources. Some of it is primordial heat, the residual energy from the original accretion and differentiation of the planet. Some of it comes from radioactive decay, as unstable isotopes in the rock slowly break down and release energy. On Earth, radioactive decay is a significant driver of mantle heat. Uranium, thorium, and potassium are the main contributors. So the question was, does the Mons Rumker region have unusually high concentrations of radioactive elements that could explain the extended volcanic activity? And the answer was surprising. No. The Chang'e 5 samples do not have elevated levels of radioactive heat-producing elements. Whatever kept that part of the moon hot enough to produce lava 2 billion years ago, it wasn't unusually high radioactivity. That means there's another explanation, and scientists are still working on figuring out what it is. Some researchers have proposed that the physical properties of the lunar mantle in that region allowed heat to be retained more efficiently. Others have suggested tidal heating, the gravitational squeezing that Earth exerts on the moon, might have played a more significant role in the moon's thermal history than previously assumed. Still others have pointed to the possibility that there are chemical differences in the deep mantle that affect how heat is distributed and retained. None of these explanations is fully satisfying on its own, and that's exactly what makes this so interesting and so significant. The data China is bringing back from the moon is not confirming our existing theories. It's challenging them. Now let's talk about the thing that is generating the most concern among planetary scientists. The thing that, when you really sit with it, starts to feel deeply unsettling in the best possible way. Beneath the lunar surface, in certain regions, there is something that shouldn't be there, something massive. This was actually detected not by China's rovers, but through a combination of data sources, including gravity measurements collected by NASA's Grail mission and ground-penetrating radar from lunar orbiters. But China's missions have added critical new pieces to the puzzle, and it's the synthesis of all this data together that is pointing towards something extraordinary. The South Pole Aitken Basin, where Chang'e 4 landed, is hiding an enormous anomaly beneath its floor. A mass concentration, what scientists call a mascon, that is unlike anything we've seen elsewhere on the Moon or on any other rocky body in the solar system. Mascons are not new. They were first discovered in the 1960s by tracking how the orbits of lunar spacecraft were subtly perturbed as they passed over certain regions. The Moon's gravitational field is not uniform. Dense material beneath the surface creates stronger gravitational pulls in specific areas, and these pull on passing spacecraft, causing small but measurable changes in their trajectories. By precisely tracking many orbits, scientists can map the Moon's internal mass distribution. The mascon under the South Pole Aitken Basin is huge, and when researchers modeled what could be causing it, they concluded that the most likely explanation is a massive concentration of dense material buried in the lunar mantle beneath the basin floor. We're talking about a structure with a mass of more than 2 quadrillion kilograms. That's a number so large it barely means anything in everyday human terms. Just appreciate that it's a substantial fraction of the total mass of the Moon itself, buried in a concentrated region beneath this ancient impact basin. The leading theory for what this mass might be is the remains of the asteroid that created the basin in the first place. When that enormous impactor slammed into the Moon billions of years ago, the Moon's crust and upper mantle were liquefied by the impact energy, and the dense metallic core of the asteroid may have sunk down into that molten material, getting stuck in the slowly solidifying lunar mantle before it could migrate all the way to the Moon's core. If that's true, we have the core of an ancient asteroid frozen inside the Moon, preserved like an insect in amber for billions of years. Think about that for a moment. Somewhere beneath the surface of the Moon, there is a piece of another world, an ancient planetesimal from the early solar system, its rocky exterior long since obliterated by the impact, but its dense metallic heart still intact, still sitting there in the lunar mantle, waiting. But here's where it gets even more interesting, because that asteroid core explanation, compelling as it is, may not fully account for the mass of the anomaly. Some researchers think the mascon is too large, too dense, to be explained by the impactor alone, which raises the question of whether there's additional material down there, material that didn't come from the asteroid, material that came from the Moon itself. And that's where the mineral data from Yutu-2 comes back into play. Because if the mantle composition in this region is different from what we predicted, different in ways that suggest denser, more iron-rich minerals, then the mantle itself may be contributing to the gravitational anomaly. The Moon's interior, at least in this region, may be structured in a way that our models don't account for. Put it all together, and what you have is a picture of the lunar interior that is significantly more complex, more mysterious, and more scientifically rich than we ever anticipated. The Moon is not a simple, uniform ball of rock. It's a geologically complex body with a complicated history that we are only beginning to piece together. And none of this would be quite so urgent if it weren't for one thing. We're planning to go back. Human beings are planning to return to the Moon and, eventually, to stay there. NASA's Artemis program has the explicit goal of establishing a sustainable human presence on the Moon. That means building infrastructure on or near the lunar surface. Habitats, power systems, landing pads, storage facilities, eventually full-scale bases. The Moon is being talked about not just as a destination to visit, but as a place to live and work. And if you're going to build a base on the Moon, you need to know what's under your feet. You need to understand the local geology. You need to know whether the ground is stable. You need to know what resources are available. You need to know whether there's water ice that can be harvested for drinking water and rocket fuel. You need to understand the radiation environment, the thermal environment, the seismic activity. All of that depends on knowing what the Moon is actually made of and how its interior works. China's discoveries complicate that picture significantly, and not in a reassuring way. Let's start with the question of lunar seismicity. For most of the Apollo era, scientists thought the Moon was essentially seismically dead. Yes, there were moonquakes, detected by seismometers left on the surface by Apollo astronauts, but they seemed minor, infrequent, and poorly understood. The Moon was considered far less seismically active than Earth. Recent analysis of old Apollo seismic data has painted a more complicated picture. Deep moonquakes do occur, regularly, at depths of 700 to 1,200 kilometers below the surface. They appear to be tidally driven, triggered by the gravitational interaction with Earth as the Moon moves through its orbit. Shallow moonquakes also occur, closer to the surface, and these are more energetic. Several of these shallow moonquakes recorded by Apollo instruments registered at magnitudes that would be considered significant earthquakes on Earth. One event in 1972 lasted for more than 10 minutes and produced ground motion that scientists described as ringing like a bell. That last detail, the Moon ringing like a bell, was initially taken as evidence that the Moon is very dry and rigid inside, with seismic waves propagating efficiently through cold, solid rock. But our new understanding of the lunar interior suggests the story is more complex. A mantle with unexpected mineral compositions, a possible buried mass anomaly, regions of extended volcanic activity. All of these complicate the picture of what the Moon's interior looks like and how seismic energy moves through it. For a future lunar base, this matters enormously. If you're building structures on or under the lunar surface, you need to know whether the ground is going to shake. You need to know how often it shakes, how hard, and what triggers it. You need your foundations and your pressure seals and your support structures to be designed to handle the right threat. And if our models of lunar seismicity are based on an incorrect understanding of the Moon's internal structure, then those designs could be dangerously flawed. Then there's the question of water. The presence of water ice on the Moon, particularly at the lunar poles in permanently shadowed craters, has been one of the most exciting and practically significant discoveries in recent decades. Water ice can be mined and processed into drinking water for lunar inhabitants, or electrolyzed into hydrogen and oxygen to produce rocket fuel. In situ resource utilization, using materials already present at a destination rather than hauling everything from Earth, is considered absolutely essential for making long-duration space exploration economically viable. China's missions are contributing important new data about the distribution and character of lunar water. Ground-penetrating radar on the Yutu-2 rover has revealed subsurface structure in the von Karman crater with unexpected complexity. The radar signals bounce back from subsurface interfaces at various depths, indicating distinct geological layers with different physical properties. The stratigraphy, the layered geological structure beneath the landing site, is more intricate than anyone anticipated. There are layers that weren't predicted, boundaries that don't correspond to what our models said should be there. And while the radar data alone can't directly confirm the presence of water ice, understanding the subsurface stratigraphy is critically important for planning any future drilling operations. If you want to extract water ice from beneath the lunar surface, you need to know where to drill, how deep to go, what you'll encounter on the way down, and whether the geology is stable enough to support drilling operations. Surprises underground are bad, they're expensive, they're dangerous, they can be mission-ending. The data coming back from China's missions is revealing that the lunar subsurface, at least in the regions studied so far, is more geologically complex than our existing models suggested. That's not a reason to panic, but it is a reason to go back to the drawing board and refine our understanding before we commit to building permanent infrastructure on or under the lunar surface. Now let's talk about something that goes beyond practical concerns and into the realm of the deeply fundamental. Because what China's discoveries are ultimately poking at is one of the most basic questions in planetary science. Where did the Moon come from? We talked earlier about the giant impact hypothesis, the idea that the Moon formed from debris ejected when a Mars-sized body called Theia collided with the early Earth. It's been the dominant theory for decades, and it's not a bad theory. It explains a lot, but it has always had problems, nagging inconsistencies that wouldn't go away no matter how carefully scientists refined the model. One of the biggest problems is the isotopic similarity between Earth and the Moon. Isotopes are different versions of the same chemical element, distinguished by the number of neutrons in their nuclei. Different bodies in the solar system formed from material in different parts of the protoplanetary disk, and the isotopic ratios in that material vary from place to place. Earth has a specific isotopic signature, and you'd expect Theia, having formed in a different part of the solar system, to have a different isotopic signature. If the Moon formed primarily from Theia's debris, as the original giant impact hypothesis suggested, then the Moon should have a different isotopic signature from Earth. But it doesn't. The Moon and Earth are isotopically almost identical, suspiciously identical. So identical that some scientists have questioned whether the standard giant impact model can be right. Various modifications to the theory have been proposed. Maybe Theia formed in the same region of the solar system as Earth and happened to have a similar isotopic signature. Maybe the impact was so energetic that it completely homogenized the material from both bodies, erasing any differences. Maybe the Moon formed mostly from Earth's own mantle material, rather than from Theia. All of these are possible. None of them is fully satisfying. And now, layered on top of those existing problems, we have new data from China suggesting that the lunar mantle is compositionally different from what we expected, that the Moon stayed volcanically active far longer than it should have, that there's a buried mass anomaly beneath the Moon's largest impact basin that is reshaping our understanding of the Moon's internal structure. Each of these individual discoveries is significant. Together, they're suggesting that our model of the Moon's formation and evolution is incomplete in ways that we are only beginning to understand. And there's something almost poetic about this. The Moon is our nearest neighbor in space. It's close enough that we can see surface features with the naked eye. Human beings have walked on it. We've driven rovers across it. We've brought back hundreds of kilograms of its rocks. And yet the more we study it, the more mysterious it becomes. Every answer seems to come with 3 new questions attached. That's not failure. That's science working exactly the way it should. But it does mean that the Moon is going to keep surprising us, and for a species that is actively planning to build homes there, surprises are something we need to be ready for. Let's zoom out and think about the geopolitical context here, because that context is impossible to ignore. China's space program has advanced with remarkable speed. In the span of roughly 2 decades, it has gone from launching its first astronaut to landing on the far side of the Moon to returning lunar samples to Earth. The Chang'e program's next missions are even more ambitious. Chang'e 6, which launched in 2024, targeted the South Pole Aitken Basin specifically to bring back samples from that enigmatic region, samples that could help directly test the hypotheses raised by Chang'e 4's mineral discoveries. Chang'e 7 is planned for the lunar South Pole, the region that is a primary target for NASA's Artemis program, and that both nations see as critically important for future resource extraction. China has also announced plans for an international lunar research station, a permanent base on the Moon. Russia has signed on as a partner, and China has been actively recruiting other countries to join the program. Meanwhile, NASA's Artemis program has faced its own challenges: budget pressures, technical delays, political uncertainty. The development of the Space Launch System and the Orion capsule have taken longer and cost more than anticipated. Landing astronauts on the Moon, originally targeted for the mid-2020s, has been pushed back. Commercial landers developed by companies like SpaceX and Intuitive Machines are part of the plan, bringing new players and new uncertainties into the equation. The race back to the Moon is real, and China is not just participating in that race. In some respects, it is leading it, not in terms of putting humans on the surface, not yet, but in terms of the scientific understanding being developed of the Moon's surface and subsurface. China is generating data that the rest of the world is scrambling to analyze and incorporate. And that matters, because the nation or coalition that best understands the Moon will have a significant advantage in establishing a sustainable presence there. Knowledge is infrastructure. Understanding the lunar geology, the subsurface resources, the seismic environment, the optimal sites for base construction. All of that is as important as the rockets and the spacesuits. You can't build a successful lunar base on incorrect assumptions, and right now, China is in the process of correcting some very significant assumptions. There's also the question of resources. The Moon is not just scientifically interesting, it is potentially enormously valuable. Not primarily because of rare metals or exotic minerals, although those may be present in interesting quantities. The most immediately valuable resource on the Moon is water, and by extension, oxygen and hydrogen, the components of rocket fuel. But beyond water, there's another resource that has attracted enormous attention. The Moon's surface is rich in helium-3, a rare isotope of helium that is extremely rare on Earth, but has been accumulating in the lunar regolith for billions of years, deposited by the solar wind. Helium-3 is a potential fuel for nuclear fusion reactors of a specific design. Now, commercial fusion power using helium-3 is still very much a technology of the future. But if and when it becomes viable, the Moon's helium-3 reserves could be extraordinarily valuable. China has explicitly discussed helium-3 as a long-term motivation for its lunar program. This is not a short-term economic calculation. It's a very long-term strategic one. But the Chinese government has a track record of making very long-term strategic investments and sticking with them through administrations and budget cycles in ways that democratic governments sometimes struggle to match. Understanding the distribution and accessibility of helium-3, which is embedded in the top layer of the lunar regolith, requires understanding that regolith, its depth, its composition, how it varies from region to region, how it has been mixed and modified by billions of years of micrometeorite impacts. The data that China's missions are collecting about the subsurface structure of the Moon is directly relevant to any future resource extraction effort. But let's come back to the purely scientific story, because it's remarkable enough to deserve more attention. One of the most intriguing aspects of the subsurface data from Yutu-2's radar is what it tells us about the history of impacts in the von Karman crater. The radar has revealed a complex layered structure in the upper few hundred meters of the lunar subsurface. There are distinct layers, each with different radar reflectivity properties, indicating different physical characteristics. Some layers appear relatively uniform, others are fragmented and chaotic, possibly indicating ancient impact gardening events, where repeated meteorite impacts have churned and mixed the surface material. Underneath those layers, the radar picks up a structural complexity that the team found difficult to explain. There appear to be large, irregular features at depth that don't correspond to simple layering. Some researchers have interpreted these as the remnants of ancient impact ejecta, material thrown out by past collisions that settled unevenly on the crater floor. Others have suggested that volcanic processes may have contributed to the subsurface complexity, consistent with the evidence from Chang'e 5 that the Moon remained volcanically active longer than expected. The point is that the Moon's shallow subsurface is not a simple, uniform stack of geological layers. It's a complicated record of billions of years of impacts, volcanic events, and other processes. And that complexity matters for anyone planning to excavate or drill into the lunar surface. It also matters for understanding the Moon's thermal history. The layering of the subsurface is partly a function of how heat has moved through the lunar interior over time. The way those layers formed and were subsequently disrupted encodes information about the temperatures the subsurface has experienced. And that information can help us test our models of how quickly the Moon cooled, how long volcanic activity persisted, and what the current thermal state of the lunar interior might be. Because here's something that doesn't get enough attention. We don't actually know if the Moon's interior is completely cold and inert today. The evidence from Chang'e 5, showing volcanic activity as recently as 2 billion years ago, tells us that the Moon was geologically active far more recently than we thought. But 2 billion years is still a very long time. Does any residual heat remain? Is there any possibility of ongoing geological activity? The seismic data from the Apollo era suggests the Moon is not entirely dead. Those deep moonquakes, occurring regularly at great depth, are still happening. They're not volcanic as far as we can tell, but they do indicate that the Moon's interior is not simply a cold, rigid ball of rock. There is still something dynamic going on down there. Future seismic networks on the Moon, which both NASA and China have plans to deploy, will help answer these questions. But those networks will only be as useful as our underlying models of the Moon's interior, and those models are currently being significantly revised in light of the data coming back from China's missions. There's one more piece of this story that we haven't discussed yet, and it's perhaps the most profound of all. If the giant impact hypothesis is correct, and if the Moon formed primarily from material torn out of the early Earth's mantle, then studying the composition of the Moon's mantle is, in a very real sense, studying the ancient composition of Earth's own interior. The Moon is a time capsule, a frozen snapshot of what the early Earth looked like, at least in its outer layers, before 4.5 billion years of geological activity churned, mixed, and recycled that material in our own planet. Earth's geological activity is relentless. Plate tectonics continuously recycles the crust. Volcanic eruptions bring mantle material to the surface, but that material has been modified by billions of years of mixing. The rock that forms Earth's mantle today is very different from what it looked like when the solar system was young. Finding an unaltered sample of that early mantle material here on Earth is essentially impossible. But if the moon's mantle represents that ancient material, preserved in something closer to its original state by the moon's relative geological quietude, then the mineral discoveries from Chang'e 4 aren't just telling us about the moon. They're telling us about the early Earth, about what our planet looked like in its infancy, before life existed, before continents formed, before the oceans filled. That is an almost incomprehensibly profound scientific opportunity, and China's missions are beginning to unlock it. Of course, the caveat is that we need to understand the moon well enough to correctly interpret what its mantle composition tells us. If our models of how the moon's interior evolved are wrong, then our interpretation of what the moon's mantle composition tells us about the early Earth could also be wrong. Getting that interpretation right requires exactly the kind of detailed, ground-level investigation that China's Chang'e program is conducting. So we're at a fascinating moment, a moment where new data is challenging old assumptions and forcing a wholesale reconsideration of things we thought we understood. The moon, which generations of scientists studied and believed they had largely figured out, is turning out to be far more complex, more mysterious, and more scientifically rich than anyone expected. And China is driving that realization. Now, it would be too simple to frame this purely as competition. Science is collaborative at its core. Chinese researchers publish their findings in international journals. Scientists around the world analyze and build on those findings. The discoveries made by Chang'e 4 and Chang'e 5 have been incorporated into the research programs of scientists in dozens of countries, including the United States. Good data is good data, regardless of what flag is painted on the spacecraft that collected it. But competition is also real. The decisions about where to land, what sites to prioritize, what questions to ask, what resources to target, those decisions are being made in a context shaped by national interests and strategic priorities, not just pure scientific curiosity. And the nation that has the most comprehensive scientific understanding of the moon will be better positioned to make those strategic decisions wisely. NASA understands this. The Artemis program is not just about planting a flag and taking a selfie. It's about establishing a long-term presence and developing the knowledge and capabilities needed to make that presence sustainable and productive. But establishing that presence requires the kind of detailed subsurface knowledge that only ground-level exploration can provide. Remote sensing from orbit can tell you a lot, but it can't substitute for actually going there, drilling, sampling, and measuring. The Commercial Lunar Payload Services Program, through which NASA is funding private companies to deliver scientific instruments and experiments to the lunar surface, is partly aimed at addressing this knowledge gap. Intuitive Machines successfully landed a spacecraft near the lunar South Pole in 2024. More missions are planned. The Artemis astronauts themselves, when they eventually land, will conduct geological fieldwork and collect samples. But China is already there, already building up its database of lunar surface and subsurface knowledge, already defining new questions, and the pace of Chinese lunar exploration shows no signs of slowing down. There's also the question of international norms for lunar activity. The Artemis Accords, championed by the United States, establish a framework for responsible behavior in space, including on the moon. Many nations have signed on. China has not. China is developing its own framework through the International Lunar Research Station Initiative. This divergence matters because the moon, unlike most of the places humans have explored, is a place where human activities could genuinely conflict. If multiple nations are trying to extract resources from the same permanently shadowed crater at the same time, questions of access, interference, and rights become very real very quickly. Getting those questions answered cooperatively, before boots are on the ground and interests are fully committed, is important. And getting them answered wisely requires everyone to be working from the best possible scientific understanding of what the moon offers and what's at stake. The discoveries beneath the lunar surface that China's missions have uncovered, the unexpected mantle composition, the buried mass anomaly, the evidence of extended volcanic activity, the complex subsurface stratigraphy, all of these are scientific findings first and foremost. But they carry practical implications that reach from the theoretical to the intensely pragmatic. For planetary scientists, they open new questions about lunar formation and evolution, about the early solar system, about how rocky bodies develop and cool and change over geological time. For future lunar explorers, they reveal a moon that is more geologically complex and less well understood than we assumed, demanding more investigation before permanent infrastructure is built. For space agencies and governments thinking about the long-term future in space, they serve as a reminder that our knowledge of the moon is still far from complete, and that the nation investing most seriously in filling those knowledge gaps is currently China. And for all of us, they underscore something that tends to get lost in the day-to-day noise of news cycles and political debates. The universe is deeply, fundamentally, profoundly strange and surprising. The thing hanging in the sky that human beings have looked at since before we had language, that shepherded our calendars and our tides and our myths and our imaginations for our entire existence as a species, is still holding secrets, still revealing surprises, still refusing to be fully known. We thought we understood the moon. We were wrong, and that's wonderful. There's a certain kind of intellectual humility that the best scientists carry with them always. An awareness that what we know is always a small island surrounded by a vast ocean of what we don't know, that our models are always simplifications, that our theories are always provisional, that the data has a way of surprising you when you actually go and look closely at the thing you thought you understood. China went and looked closely at the moon, and what they found has sent ripples through the entire scientific community, challenged models that had been comfortable and settled for decades, and reminded everyone paying attention that the moon is not done with its revelations. The subsurface of the moon is speaking, and it's saying things we didn't expect to hear. The buried mass anomaly, sitting deep beneath the South Pole Aitken Basin, is a remnant of a violent collision that reshaped the early lunar surface in ways we're still working to understand. The mantle minerals that U22's spectrometer detected tell a story about the moon's interior that doesn't match the chapter we thought we had already written. The 2-billion-year-old volcanic rocks from the Chang'e 5 return mission speak to a thermal history far more prolonged and complex than our models allowed for. And the layered subsurface structure revealed by ground-penetrating radar points to a geological complexity that any future lunar-based designer will need to take seriously. Each of these discoveries, individually, would be significant. Together, they constitute a revolution in our understanding of Earth's nearest neighbor, a revolution that is ongoing, with more missions planned, more samples to be returned, more data to be collected and analyzed. The picture is incomplete. We are in the middle of a process of discovery that will continue for decades. And that process is being driven, in no small part, by China's systematic and increasingly sophisticated program of lunar exploration. For NASA, for the broader international scientific community, for anyone invested in the future of humanity in space, the appropriate response is not alarm in a panic-inducing sense. It's not a reason to